Okay, so I'm back. I'm going to finish up this last question, just so that we're all still working at the same thing together here. So the question was, identify which of these reactions are redox. So if I look at the very last one here and put my oxidation numbers in, so everything's done except sulfur, and you think, well, maybe that means everything's good. But when we look at this, I can see that sulfur on the left here, I have 4 minuses here, so sulfur must be +4. And if I look on the right, I have 6 minuses and 2 pluses. Oh, I guess I need another +4 again. So this one is not a redox reaction. Okay, so we can use oxidation numbers now to decide whether things are gaining and or losing electrons, even if they really aren't gaining and losing electrons. Because remember, for those reactions there, nothing is really gaining or losing electrons. They're just kind of changing the way they share their electrons. Okay, so our last part of the note, the B part of this note, with the way I would normally do it, I usually run the package off in 2 parts. The second part here is 9.5 and 6 from the textbook. 9.5 and 9.6. Okay, so we're going to start off with this looking at the redox that goes on with metals. Now, a lot of metals have the ability to react with oxygen, so we've come up with a generic name for types of reaction we're talking about, and that's called corrosion. So corrosion is a type of redox reaction that involves between any metal and substances that are around it. Now in the environment, that means for us, we typically think of outside in a forested area, but environment to a chemist means anything that's surrounding the metal. Now, corrosion itself is an expensive problem for humanity, right? Because we have developed over the course of since the Industrial Revolution, we've started making tools with metals. And we have, I guess, obviously weapons originally with metals too. We also have lots of equipment with metals. Our cars are metals, all of our construction equipment are all metals. And what happens is over time, the metals get weaker because they react with oxygen in the air. And as they do that, a lot of them form rust. So rust is one type of a corrosion reaction. Rust specifically talks about the reaction that occurs between iron and oxygen. Iron is in steel, and it forms iron 3 oxide. Iron 3 oxide is a problem because it is that red, weak, flaky material that forms, and it has no strength. So if I start off with steel and I turn to this red flaky stuff, you can actually almost powder it in your fingers as iron 3 oxide. That's not a good thing. So if I again just quickly look at the oxidation numbers, I see iron here is 0, oxygen is 0, oxygen here is -2, and the iron would have to be, I've got 6 minuses, so I need 6 pluses, but there's 2 irons, so it's +3. So how do I go from 0 to +3? I have to gain positives or lose electrons, Leo. So the iron is being oxidized. Okay, that's what's going on here. Now, originally that word oxidation came from the fact that most of the reactions we studied going back historically were reactions of things with oxygen, but we now know if I react iron plus sulfur, I'll make iron 3 sulfide, and it's still an oxidation reaction, even though there's no oxygen involved. All right, so that word oxidation is a little bit of a maybe a misnomer, but that's okay because we know what we're talking about. Right? We're talking about things that are having electron transfer. Now, like I said, part of the problem for us as a society is that this is a very expensive problem. Right? It's a very expensive problem, and It's why people have to buy new cars. It's why people have to buy new bicycles. People have to replace all kinds of equipment and things that are outside or exposed to the elements, because with water and weathering, it exposes parts of the surface of metal that leads to more and more corrosion or rusting, if we're talking specifically about metals. So what can I do to try to slow this down? Well, if I want to slow it down, if I can put a barrier between the metal and the air that's going to oxidize it, then I can at least slow down the process, if not stop the process. So what can we put between the metal and the air? Well, I can put 1 coat, 2 coats, 3 coats, 4 coats, 5 coats of paint, right? And again, when you buy an expensive car, one of the reasons why some cars are $25,000 and some cars are $125,000, part of it has to do with the quality of the parts. Some of it has to do with the quality of the metal. Some of it has to do with the fact that they put so many coats of paint on an expensive vehicle, and that way it reduces the risk of corrosion, and it also gives a longer life out of the finish on the car. The other thing that you can do is you can spray the underneath of the car, sometimes with an undercoating material that's often an oily base or a waxy base material, right? And what that does is it coats the surface of the metal, and that coating creates a barrier between the oxygen in the air and the iron that's in the steel. Okay, so corrosion is a real problem, and again, people don't really like the way things look when they're rusty either. It's not just the fact that it's going to get weaker over time, but it kind of looks not so good. Okay, so if the goals here are to cover the metal, all right, that's one way of doing it. The other way is to cover the metal with another metal, and basically I'm going to have a metal adhered to or melted right onto the surface of the steel that is either less reactive than the metal or more reactive than the metal. Now, when we use what we used to call tin cans, right? We don't. If you go and get a can of soup at the grocery store, or a can of tomatoes at the grocery store, we say it comes in a tin can. Well, it's not a tin can. It's a steel can that has a tin coating on it, right? So tin is an element on the periodic table, right? And when I take my metal and I create, so here's my steel, and I've got my tomatoes inside here. Tomatoes are quite acidic, so the acidity will react with the steel very, very quickly and destroy the can. It will actually eat right through the can. So we put a layer of tin on the inside here, and that layer of tin basically protects the surface by creating a barrier. Now, the problem with the tin is it only creates a barrier as long as it's intact. If I've got a leak in it, it's like having a leak in your tire. The tire will hold air until you've got a small hole, and the same thing happens here. I will have a good barrier, a good seal. I don't know if I've got the textbook here or not. There it is. Oops. Okay, so here's the iron that's in the can, and I'm going to take a layer of tin now and put it across the surface of the steel. But again, if I get a crack in that tin, then the contents can now get inside and they start eating away at the metal and ultimately making the metal weaker and weaker. That also means some of the iron oxide, which is rust, can actually get back up into your food too. So if you are buying groceries at the grocery store that come in steel cans, if you find one that's got a dent in it, it's not a great idea to take the dented can. Sometimes they take the dented cans if you work in a grocery store, or if you've done grocery shopping, you find a little shelf at the back of the store with cans on it, Some of them are on the back shelf at the store, and they're cheap. Like, they make them less than half price. And why is this so cheap? Because someone dropped the case, and there's some dents in the can now. And what that dent does is it creates a little crack in the tin on the inside. You can't see it. And what's happening is now the food that's on the inside is exposed to the iron that's in the can. Right? So there's one possibility, right, where we can use a metal that is less reactive than the iron that we're trying to protect. The other option are to use elements that are more reactive than the metal. So zinc and magnesium are more reactive than the metal. And what happens is, when you think, well, why would I put something that's more reactive than iron? It's going to cause more and more trouble. Well, what happens here is, again, if here is my steel can, and now I put a layer of zinc on top, what's going to happen is that zinc is going to get oxidized. It's going to turn into zinc oxide or magnesium oxide. And what happens is that forms a very, very, very hard, that zinc oxide coats the zinc with a very, very hard material that even protects the zinc from further oxidation. So I now have my steel, which is intact. I've got a layer of zinc, which has oxidized on the surface with zinc oxide, and the zinc oxide will basically protect the zinc, which protects the iron. The same thing can happen with magnesium. They often do this with the bottom of metals that are exposed to salt water, because salt makes this reaction go faster. The salt basically doesn't cause the rusting to happen, but the salt acts as a catalyst to make the reaction go faster. Right? So things that are exposed to salt water, or even fresh water, but mostly salt water, will basically rust very, very fast. So they'll often put, these are called sacrificial metals, because we know that they're going to ultimately they're going to get used up. But if I put it at the bottom of a boat, what it will do is it will form that barrier of zinc oxide or magnesium oxide on the bottom of the boat. But over time it gets worn away, and then you'll ultimately have to recoat it, right, to replace that layer. Right. So those are kind of some applications for redox. Now, you think, well, how do I know which elements are more reactive than iron and which ones are less reactive than iron? Well, we talked earlier in this course about the activity series for metals. We used this when we were talking about, will a single displacement reaction happen or not? And we looked at this type of reaction that I'm just going to review one more time here, because it helps us to decide what kind of metals we can use for our sacrificial metals, for those that are more reactive than the iron that goes in our steel. Now, we talked earlier in the course about the fact that jewelry is basically made from elements that are very unreactive, which means they won't rust, they won't react with your skin, they won't react with your sweat, they won't react with the water when you're doing dishes or laundry or having a shower. They're very, very unreactive. And we know on our activity series, let me just pop up the activity series here. Remember, the activity series is a way to look at how reactive elements are. So I've got most reactive at the top of this series and least reactive down here at the bottom. And again, notice that our jewelry metals, gold, then platinum, then silver, platinum's not on here, are very unreactive. And those at the top are very reactive. Lithium, potassium, barium are very reactive metals. Okay, so the reason why the activity is so different is because how easily it is to lose electrons. So the elements up here at this end up here, are easily oxidized. They can lose electrons very, very, very easily. Right? These ones will not lose electrons unless something else comes along and takes them from the elements. Okay, so let's go back up to, so we know, like I said earlier, that our jewelry is made from unreactive metals. If I drop, like I said, if I drop elements or metals that are made out of unreactive metals into a weak acid or dilute acid, they won't react. But if I dropped just a steel paper clip in, right, the iron that's in there will actually dissolve over time. You come back and you say, where'd my paper clip go? You think, wow, that acid ate my paper clip. That must be crazy strong acid. Well, vinegar would do it. And it's not that strong, right? We eat it. Right? But what happens is the vinegar will basically force the iron in the paper clip to undergo oxidation, and ultimately it will turn to iron oxide and it will dissolve. So we know about the activity series. Like I said, we've used it before, and we're going to use it again one more time here before we finish up chapter 4. So if I look at the ones that are the least reactive in the series, they're the ones that do not oxidize. Right? So the most reactive are easily oxidized. The least reactive will not easily be oxidized. Right? And the reason is the ones at the top lose electrons very, very easily. The ones at the bottom will hold onto their electrons. If anything, they will steal electrons from elements that are higher on the list. Okay, so let's look at example here. So if I took a piece of copper, so you see I've got a piece of copper here, and I'm going to wind the end up into a bit of a coil, and I'm going to drop it into a solution of silver nitrate. Silver nitrate dissolves very well. So here this looks like water, but it's actually got water with silver nitrate dissolved in it. So there are silver ions in here. And I've got elemental copper. And what's going to happen is the copper is going to lose electrons to the silver, and the copper will be oxidized, and the silver will be giving its electrons to copper. Copper is gaining electrons, so the copper is Gur. So the copper is being oxidized. The silver is gaining electrons, and the copper is losing electrons. Okay, so that being the case, if I look at what's going on in my beaker here, I can see that the color of my solution is turning blue. That means there are copper ions in solution because copper ions are blue. Even though the metal itself is that orangey, reddy orange color, when it turns into dissolved copper ions, they turn blue. And the silver, which is metallic, is forming on here. You can't see it because it's underwater. But if I was to take it out, it'd be nice and shiny, and it would be elemental solid silver. And if I just it actually comes off in chunks. So if I took that copper wire and lifted it out of here, and took the bottom part and kind of banged it on the table a couple of times, big chunks of silver would come off. And silver is a valuable metal, right? So that would be, That would be one way to show a redox reaction. Now, if I used nickel ions in here and tin foil, right, and I left it and came back the next day, unlike this one here that has undergone a redox reaction, nickel and tin foil will not undergo a redox reaction because of the location of nickel and tin in the activity series. Okay, so let's look down to a couple of examples here, and this is similar. We did these already once when we were doing qualitative chemistry earlier in the course, back in chapter 2, I believe it was. So the question is, predict whether this reaction will happen. So I'm going to write the reaction. Aluminum foil and silver nitrate. Aluminum plus silver ions. Okay, again, the nitrate is just a spectator. And what's going to happen is I might get silver. Well, let's write it actually out. Silver nitrate. And what I should get is a single displacement where the aluminum is going to kick the silver off, and the aluminum is going to replace the silver to make aluminum nitrate. Now, aluminum is a 3 plus ion, and nitrate's minus 1. So the 1 comes down and the 3 comes down, so there becomes my silver nitrate. So the question is, will this reaction happen, yes or no? Well, I'm going to look back to my activity series, and just a way to remember, just the way that I remember, is I always look at the activity series and I say, which of the two elements is higher on the list, aluminum or silver? Well, I know silver's at the bottom of the list because it's jewelry. So silver and gold, I always remember they're at the bottom. So the aluminum is up here. Silver is down there. So the higher one wins the battle. Okay, so the aluminum. So does the silver get the nitrate or the aluminum get the nitrate? The aluminum gets the nitrate because it's higher on the list. So the answer is yes, this reaction will happen. If I put copper in an iron 2 sulfate solution, copper plus iron 2 sulfate, iron is 2 plus, sulfate is 2 minus, the 2's come down and the 2's cancel out. So there's my iron 2 sulfate. The products will be copper sulfate. It can be either copper 1 or copper 2. Copper 2 is much more common, so usually remember when we're trying to decide which one will form, look for the one that's more common. So copper would be a copper 2, sulfate would be minus 2, the 2's come down and cancel out, and I'm going to get iron. So the question is, which one's going to win the battle for the sulfate, the copper or the iron? So again, go back up to the list. I can see copper is at the bottom down here, iron's higher up, so iron's going to win the battle. So the iron is going to win the battle on this side over here. So the answer is no, this reaction will not happen, right? They will sit there and look at you, right? And nothing will happen inside that beaker. If I move down to the last one, if I put a piece of zinc in a solution of hydrochloric acid or 8 hydrogen chloride, I'm going to get the zinc will kick off the hydrogen, so the hydrogen will become H2, and the zinc will join the chloride, and zinc is a +2, chloride's a -1, so the 1 and the 2 come down, and the question is, which is higher on the list, hydrogen or zinc? So again, back to our list. So hydrogen's way down here, and you think, well, why is hydrogen here? Everything else on this list is a metal except hydrogen. But again, think where hydrogen is on the periodic table. We've actually got it on the left top corner of the periodic table. It's not right beside helium. It's on the opposite side where all the metals are. So hydrogen often has properties that make it act as if it wants to be a metal. So it's actually on the list here. And I had hydrogen and I can't remember what my other element was now. Too busy talking. Hydrogen and zinc. Okay, so hydrogen is here. Oops. Hydrogen is here, and the zinc is here. Zinc is higher, so zinc's going to win. So zinc's going to get the chloride. And it's on the right side over here. So the answer is yes, this reaction will happen. Okay, so the last one, there's an example there. It says, use the activity series to decide whether a chemical reaction will occur if lead is placed in a solution of silver nitrate. So I've got lead and, silver nitrate. Make my pen a bit bigger. Now if it reacts, the silver should come off, and the lead should join the nitrate. And the most common ion for lead is lead 2. So the question, which is higher, silver or lead? So I'm going to go back to my activity series. Remember, silver is usually at the bottom, right? So the lead is way above the silver down here, so lead's going to win. Lead's going to win. So the answer is, I won't end up with silver nitrate. No, I will end up with lead nitrate because lead's higher on the list. So the answer is yes, this reaction yes, this reaction will happen. Okay, so I'm going to stop there. There are some questions, A, B, C, D, and E, which are right here. So I'm going to get you to work on those questions, A to E, and then we're done this section of the text. So I'll get you to do questions 1 to 6, which are on page which are not on any page. They're down here below. So you can do these 1 to 6, 1 to 3, and 6, and then you can actually start working on the review for Chapter 9, and I've left you with specific questions to work on down here. Okay, so again, remember we're not having a Chapter 9 test. We're going to have a 9 and 10 test together towards the end of next week. If it's not Monday the following week, it'll be probably the end of next week, Thursday or Friday. All right, so I haven't figured out Chapter 10 for next week yet, but that's where we're at. Okay, so take care, everybody. Keep at it. We're in the home stretch, right? Probably got 4 notes left before we end the semester. So stay on top of your homework.